Hi everybody. Let's get back to our problem. Solid state electronic devices series 5, and this is going to be a problem from chapter 5. Let's get started with this is the homework assignment that I had. So we have our 5 problems, some of them from our textbook. Let's get started with problem number 1. As you were, for lower concentration, constant total amount phosphorus diffusion in silicon at 1000 degrees Celsius, find the percentage change of phosphorus concentration of a sample surface for A. 1% variation in diffusion time, B. A 1% variation in diffusion temperature. Assume that the temperature dependence of the diffusion constant in the process is corresponds to this equation. D, that's the temperature dependent, that's absolute temperature, equal to D0 exponential negative EA over kBT, where the activation energy EA equal to 3.66 electron volt. Hint, approximate relevant delta C over C by dC over C. So this is the guideline for you to be able to solve the problem. However, the main point is that as you find the percentage change of phosphorus concentration, where you have a 1% variation in diffusion time, so the time change. And for B, this is the temperature change. However, when the total number of impurity is limited to a fixed number or limited source, then their distribution is approximated by a Gaussian function described by C. This is the number of impurities in the unit of per cubic centimeters, and equal to S over square root pi dt exponential negative x squared over 4 dt, where S is the total impurities initially deposited near the surface per area. D is the diffusion constant and become a function of temperature and dopant type. T is the time of diffusion. For A, that suggests you to do the derivative of the impurities concentration rate, C, with respect to time, because you want to see what happened when the time change. So when you're talking about the time, so you just let's place x equal to 0, so you don't have an exponential term. You simply have C equal to S over square root pi dt, and you do a derivative, and that's give you this expression. Then you apply the percentage change of the phosphorus concentration. You simply divide dC, that's the variation of impurities concentration rate, divided by impurity concentration, and you end up with this expression. Now for your time turn out to be let's get back to the previous page. 1% variation of in diffusion time. So that means you will put the time to be 0.01 t. That's the 1% of the diffusion time, right? And when t cancel out, because you divide dc by c, that's give you a negative 0.005 or 0.5%, where negative sign means the P concentration decreases with increasing time. Now let's work out on the temperature. For part B, they want you to see 1% variation in diffusion temperature. And you follow the same step. You start with impurities concentration C, and simply differentiate your impurity concentration with respect to temperature, absolute temperature. And you have to keep T. That's the exponential term, right? Let's see what I have here. Actually, let's cancel it out. So you end up with the derivative of dc, derivative of c with respect to t equal to this expression, and you divide it by impurity concentration. You end up with this expression. And for the temperature change of 1%, that's the turn out to be a 0.01 T. And just plug in the number EA, 3.66 electron volt. That's the temperature. 1,000 degrees Celsius. That's give you 1,273 absolute temperature or Kelvin. And this is your KB, 8.62 10 to negative 5 electron volt per Kelvin, and you end up with the percentage change in the phosphorus concentration by temperature, 0.1%, which is the 0.17 or 17%. Now you'll be able to compare that between the temperature and the time. So you will see that the temperature affects much more effect by time, right? This is the 17%, but for the time change or diffusion time change, that's the change the concentration only 0.5%. But this one is for the temperature change only for 1%. That's change the phosphorus concentration by 17%. So in fabrication process for doping, temperatures needed to be controlled closely. That's the main factor. Problem 5.4. And Abrupt silicon PN junction has Na, that's the accepted doping 10 to the 17th per cubic centimeter on the P side, and donor doping 10 to the 16th per cubic centimeter on the N side at 300 Kelvin. A, calculate the Fermi level, draw an equilibrium band diagram, and find V0 or the built-in function, the built-in voltage from the diagram. B, compare the result from A with V0 calculated from equation 5.8. C, calculate the equilibrium depletion width, that's the W, and peak electric field, E0 or Emax for this junction, or the magnitude of the maximum magnitude of E or electric field for this junction. Wherever you have P-N junction, where you have you have p-type doping and you have n-type doping on silicon. Let's take a look at energy band diagram. First, at thermal equilibrium, the Fermi level is constant, or the energy band diagram for Fermi level is going to be flat. 2, for Na, on the p side, you can apply this equation, because you know that you can look for EIP minus EF, the gap between the intrinsic energy level and the Fermi energy level. Sorry, that is equal to KBT Ln, the majority concentration of p-type material, over Ni, that's the intrinsic concentration. And what you need is the PP, right? From this equation, PP, that's the majority carrier concentration on the P side, equal to this expression. But you can see that for on the P side, Na much greater than Nd, so your Nd drop out, and Nd drop out. You have what? PP is the approximately Na, or just pick up your Na as the PP, or the whole concentration on the P side. That's the 10 to the 17th per cubic centimeter. Now for the inside, same. Nd equal to 10 to the 16th, and you can simply put the electron concentration on the inside to be Nd, which is the 10 to the 16th. That's give you the energy gap between EF and EI on the inside to be 0.347 electron volt. And if you add this equation together, you end up with EIP minus EIN. That's the gap between intrinsic energy of on the P side and the N side. So you just add 0.407 with 0.347. That's give you 0.754 electron volt. And this is your energy band diagram. You have EC, you have EV, you have EF, right, at equilibrium. And then on the P side, you have the gap between EIP and EF as calculated, 0.407 electron volt. And the inside, you have the gap between the EF and EI, that's the 0.347 electron volt. And this is the depletion region that you have an electric field. And also the built-in potential, actually this one going to be 0.407 plus 0.347, or 0.75 electron volt, or that's sometimes we call the potential barrier rate. So this is your energy band diagram. Now, when if you compare by using equation 858, your built-in potential equal to kBt over q ln n a or d over ni squared. Just the plug-in number, you get the same result. Become a 0.754 electron volt. For C, I ask you to find the depletion width W, which is equal to okay, just do I explain that later. For the depletion width W equal to this expression, and you end up with your W equal to 0.325 micrometer. And this is a straightforward calculation. You just need your Ks, that's the relative electric constant of the semiconductor. For silicon, Ks equal to 11.8. You need this number for calculation. And for germanium or another type of semiconductor material, the Ks is going to be different. Problem 5.5. Compare the contact potential of the silicon device of problem 5.4 from the previous problem with similarly doped germanium and gallium arsenide junctions. What trend did you notice? So we want you to work out on germanium and gallium arsenide. We were asked you to calculate for the built-in potential or the contact potential. That's the kBt, ln, na, and d over ni squared. So what different is that for different type of semiconductor materials are Ni, intrinsic electron concentration. For from the book, gallium arsenide Ni equal to 2.0 10 to the 6th per cubic centimeter, and for germanium, that's the 2.5 10 to 13 per cubic centimeter. And that's for gallium arsenide, your built-in potential 1.22 electron volt. And for germanium, you just plug in your Ni. This is supposed to be square. Sorry, my mistake. And that's equal to 0.37 electron volt. Now, for the summarization, I just compare different type of semiconductor materials. This is the silicon, germanium, gallium arsenide, and from calculation we end up with the built-in potential for each type of semiconductor to be like this, and also energy band gap. So you can see that the built-in potential is increasing when the energy band gap is there. Look like I put something wrong. Let's see for germanium. It's supposed to be higher than some. All right, this is 1.11 electron volt. I think I put this number wrong. You go back and check again. But the built-in potential increases with the energy band gap. So check out this number again. Sorry for my mistake. Problem 5.7. The junction described in problem 5.4 has a circular cross-section with diameter of 5 micrometer. Calculate xn0, the width on the inside, and the p-type material, xpo and q plus. That's the total charge for this junction at equilibrium or 300 Kelvin. Also sketch Ex, that's the electric field and charge density to scale as in figure 5.9. Well, from problem 5.4, we have xn0 equal to 0.299 micrometer and xp0 on the p side. That's the 2.99 10 to second micrometer. And you can also recalculate for xn 0 by using this expression. And also you have the relation NA xp0 equal to ND xn 0, and your depletion with W equal to xn 0 plus xp0. Now for the total charge, coulombs in the unit of coulombs, that the area multiplied by the charges, and the charges equal to Q xn 0 and D, right? And you can see that the ND has the unit of what, per cubic centimeter, right? So X has the dimension of meter and A has the dimension of meter squared. So this just gives you the number, of a carrier, and you multiply by Q. That's give you the total charge. For the cross section as the circular with the diameter is 5 micrometer, so your area become a pi r square. That's the 5/2 for r, and then you convert from a micrometer to a centimeter. You have 10 to negative fourth, and this is your Q, and this is your x n 0 as we calculated previously, and this is your ND, 10 to the 16. This is your charge, 9.38, 10 to negative 15th. Now let's go for the plot. As you plot the charge density and also the electric field along the PN junction. We were prepared for the plot. I pick up numbers from problem 5.4. NA, ND, xn0, xp0, E0, that's the electric field's max, or the magnitude of E max. Then for the end region, x much greater or equal to 0, or less than or equal to xn, you have equation Bx equal to this. And your electric field simply derivative of negative derivative of the voltage with respect to x. And you can see that this is the linear with x for electric field with the slope of Q and D are Ks epsilon 0, because the negative and negative make a positive, right? And for the magnitude of E max, where x equal to 0, you have this is your magnitude of your E max, Q and D xn over Ks epsilon 0. Same as the for P region, for x equal to or greater than negative xp and equal or less than 0. This is your Vx, and this is your E, and same, you have the slope and you have the magnitude of your E max. So actually these are the same, because you have the relation ND xn that's equal to NA xp. Now let's go to the plot. Where are we? 43. Okay, this is the P region and this is the N region. And for the charge density, you know that for ND, that's the 10 to the 16. And for your NA, this is the 10 to 17th. And you have xp0 at 2.99, 10 to negative second micrometer. And for xn0 is at 0.299 micrometer. And for electric field, you can see that on the inside, the electric field is going to have a positive slope. And on the p side, this is the negative slope, and these are slopes on each side, and this is your magnitude of your Emax. That's the 4.58 10 to the fourth centimeter. Okay, let's go over for the last problem. A germanium p-n diode has an A equal to 5 10 to the 17th per cubic centimeter and Nd equal to 10 to the 17th per cubic centimeter. Calculate the built-in voltage of V0 at 300 Kelvin. At what temperature does the built-in voltage decrease by 1%? In calculation, neglect the temperature dependence of NV, NC, and EG. The dependence is weak as compared to the main temperature-dependent components in the expression for the built-in potential. Well, for this case, the main point is that your Ni now is dependent on the temperature or the absolute temperature. So you need to take into account of temperature for Ni. VBI equal to KBTQ, you know this equation, so we calculate for the built-in potential at 300 Kelvin. I did not put the number here, you can do your own calculation, right? We have everything. We have Nd 10 to the 17, you have Na 5 10 to the 17th, and your Ni for silicon at 300 Kelvin is the 2.5 10 to 13th. And kBt over Q that are 0.0259 volt. Now, when you were taken into account as the temperature dependent of Ni, you were simply write VBI, you plug in Ni square, right? Because VBI equal to KBT over Q ln Nd and A over Ni square. So this is actually Ni square. And you have Kb over Q multiplied by, you just expand this term. So become T multiplied by ln of A, this is my A, and A and D over NC and V, and then plus ln of this term simply become EG over KBT, and T cancel out, so you don't have the second terms depend on T, so you do a derivative with respect with T of VBI. So you have KBQ, KB over Q, and then LNA. Now the VBI become KB over Q multiplied by ND and A over NC and V dt. For 1% change of the built-in voltage, that means 0 dVBI becomes the 0.01 VBI, and we have a VBI that we already calculate for. That's going to be equal to this equation dt, and you can find the temperature because dt simply is the temperature that deviate from 300 Kelvin, right? And your NC actually equal to this one. This is the effective mass of electron, and this is the effective mass of the proton, and H is the Planck constant. Okay, you can do the rest for the calculations. That's the problem of the homework number 5, and we will continue the problem assignment or the homework number 6 in the next series. Okay, bye.